Swayam Prabha. Digital India. Educated India.
Good morning, everyone. It is my honor to introduce Professor Deepak Dhar, a pioneer in theoretical physics and statistical mechanics. After completing his master's at IIT Kanpur, he pursued his PhD at Caltech. He dedicated nearly 4 decades to the Tata Institute of Fundamental Research, where his groundbreaking work on self-organized criticality and the abelian sandpile model earned worldwide recognition. In 2022, he became the first Indian to receive the prestigious Boltzmann Medal, the highest honor in the field of statistical physics. In 2023, the Government of India awarded him the Padma Bhushan for his immense contributions to science. Professor Dhar is currently serving as a distinguished professor at ICTS TIFR Bangalore and is also associated with the IISER Pune. Let us all give him a warm welcome.
Okay, so thank you very much for the kind introduction. So I will, in the next 2 days, I will tell you a little bit about the sandpile model. So why study the sandpile model? So I will discuss the sandpile model, but why worry about the sandpile model? That's the first question. And I think one should give a good answer to that question, because before we study some problem, we should be, why is it interesting to study some strange problem defined in some funny way? So it turns out that there are lots of physical phenomena which share some common features, and these features are also seen in the sandpile model. So let me just say what kinds of phenomena are there. So for example, there is earthquakes, and there are things called forest fires, and there are things called rain, and stock market even. And so all these things, which are very different phenomena, have something in common. And what is that common feature which is there in all these different systems is that they are driven. There's some external thing which provides some energy input or some such thing. And that driving is pretty steady. But the output of the system, the relaxation, is very sporadic and burst-like. Okay, so for example, in rain, water evaporates mostly from the sea at roughly constant rate throughout the day. But the water comes back from the atmosphere to earth in the form of rain. And that is very sporadic, for 24 hours nothing will happen, or even for 3 months nothing will happen. Then all of a sudden there will be a lot of rain. So the relaxation events are burst-like. They just occur, and then for a long time nothing happens. And the size of these bursts is also variable. Sometimes, there is a rain, but the rain will be 1 centimeter, or it may even be 100 centimeters in one event. So these kinds of events, in which there are lots of burst-like events of variable sizes, also occur in things like earthquakes. In earthquakes, what happens is that there is these continental plates, they keep on moving towards each other. Okay, so as they move towards each other, they build stress, and at some stage the stress becomes too much, and the rock kind of breaks or becomes powder-like, and then something happens and it causes an earthquake. But the earthquakes are very rare events, or they occur even in earthquake-prone areas. They occur once in a few months or some such thing. But the drive is very steady and constant. It is just so many centimeters per century. The continents are moving towards each other at a constant rate, but the burst-like events occur at random or very sporadically. So these kinds of phenomena are interesting to study because, we worry about earthquakes, when they will happen, or so one needs to understand when some big event will occur or how they will occur. And so we would like to understand these kinds of phenomena. Now it turns out that I can study these kinds of phenomena in any of these systems. I can study the rain, or I can study earthquakes, or I can study forest fires or some such thing. And if I understand that thing better, that will help me understand other things also. Okay? So it turns out that the system which is well studied, which is understood somewhat better, is the sand piles. And whatever understanding we get from sand piles, we can use it to understand other things. So that is my aim, is to understand all these kinds of physically interesting systems using some simple models like sand piles. Okay? The other reason for studying sand piles was because I was requested to do it, and it is that actually it turns out that lots of these properties of sand piles can be understood rather easily without using very heavy mathematics, mostly using high school mathematics. Sometimes I think we need 12th grade mathematics, but not beyond that. Of course, sometimes we need higher, but we will skip that part. And good part can be understood using just the 12th grade like mathematics. Okay, so that is, I will try to ensure that you understand, but please feel free to interrupt me if I say something which you don't understand. There is no problem. I don't have an agenda that I have to finish this much material today. You can look up, all this stuff is available on the internet, so you can always read more if you are interested. The aim is not so much to read much more, but to understand what is being said. So if you just swallow, yeah, aisa kuch hota hai, that is not good enough. And my aim will be that you actually understand those simple things quite well. Okay, very good. So first thing I want to do is to have a, so we want to understand sand piles. So all of you are actually familiar with sand piles, and of course Chennai is near the sea, next to the sea. So what is a sand pile? There are some features of sand piles which are well known and well reproducible. They occur in all kinds of different, you can make all kinds of sand. The sand is not always the same thing. There are different sands in different places. But some features are common. So first feature, which is very important, is that there is something called dry sand and something called wet sand. And these are very different. And wet sand is much more complicated to understand than dry sand. And so we will say that we want to understand sand, but start at the beginning and don't start with the more complicated thing. So the easier thing is to understand dry sand. Okay? So what do we know about dry sand? So first thing we know is that suppose you take some dry sand and you pour it out from one point on the floor below, it forms sort of like a pile like this. It is like a cone. The shape of the pile is that of a cone, and there is an angle with the horizontal. This is called the angle of repose. The pile is like that, but you should understand this is the angle of angle which the slanted line makes with the horizontal. Okay, and so this pile is actually, of course, three-dimensional. It looks like this, but this angle is the same wherever you measure along the circle. And of course, it is not really exact because as I drew, it's not a cone in the very rigorous mathematical sense, but it looks like a cone to me. Okay? And the important point about this thing is that this angle is very reproducible for the same sand. If you change the sand, the angle will change from 40 degrees to 43 degrees or some such thing. But it is quite, for the same sand, it is very reproducible. You can do the experiment or your brother can do the experiment and it will be the same. So first thing we have to understand is why is that? Because the grains are not the same, they are very different types of shapes, but this angle turns out to be the same. Okay, so let us just, right now we are working at a very qualitative level. So what people realized is that what happens is that if you make a pile like this, whose angle, you can make it by hand, whose angle is less than the angle of repose, then this pile is stable. If you put a little bit of sand on this, it will just sit there. Okay? But if you make a pile which is like this, you can make it by hand, by tapping or some such thing. Okay? But then it is unstable in the sense that if you perturb it, just drop 1 or 2 grains of sand here, poof, the whole thing will fall down. All this sand will go away and it will remain at an angle which is the angle of repose. Okay, so the system selects itself to come to this angle of repose. That is how the relaxation occurs. If the angle is more than the angle of repose, it will go down to become the angle of repose. If it is less than the angle of repose and you add something, then it will grow. And it will be, whenever you see it, it will be at the angle of repose if you are adding continuously. Okay? So that much is very simple. So people have actually done very interesting experiments on sand piles. And one experiment which I will draw sort of a picture of is like this. There is a flat circular table which looks like this, and it is connected to some something which measures the mass. Meter. It's a meter for mass. Okay, and you put some sand on it, then it will show how much mass there is in the sand. Okay, and you add sand from above. Sand from above is added sort of like this. You drop one or 2 grains at a time. Okay, and so it makes a pile which kind of looks like this. And then you keep on adding sand 1 grain at a time and the excess sand keeps on dropping out. Okay, and then you can actually, since I have this meter, and I can just plot the flux of sand as a function of time. How much sand goes out as a function of time. And it looks like this. I'm drawing schematically. So maybe there is a bigger break. So, you know, there are sometimes the sand comes out, sometimes the added grain is just stuck there, it doesn't drop down. And sometimes the events are very big, even 100 grains will drop out, sometimes only 3 will fall out. And so there is a kind of random phenomena. How much will come out now? This is kind of hard to predict. And it's like predicting whether it will come out head or tail if you spin the coin. So it will depend precisely on where you add here, whether you add it here or here, or so what happens is there is an avalanche of sand which happens. The avalanche, just 1 second. Sorry? Yeah. So there is a dry sand which is being poured at a constant rate on a circular table. Okay, and this meter measures the mass of the sand, and hence it measures how much change in sand in a given time. And so that's what I'm plotting here, is the dm by dt or delta m by delta t. Small change in mass. Every second I plot how much event has occurred, or I will add 1 grain per second and see what's the event which happens. And this is the plot of the event. And this is what we want to understand. And now already at this stage, I make the connection that suppose I'm studying earthquakes. I don't care in the complicated geology and all kinds of stuff which happens, Australia is doing this and Japan is doing that. I don't know enough geography. But if I sit at one place and I have this seismograph, earthquake meter, it has this kind of a response. Sometimes nothing happens, sometimes big events happen, and then this may be in the sand experiment, this is of the order of minutes. In the earthquake experiment, it will be years. Over 50 years, you see how many earthquakes have occurred, and they will show similar structure. And so that is what we want to understand. Okay? Just to make sure that we understand the general phenomena. So if you look at rain, it also looks like this. For rain, there are lots of phenomenological observations. One of the which you can remember is that 80% of the rain occurs in 20% of the time. If you look, actually Chennai is not very typical. I come from North India. So, like in the plains, then most of the rain occurs in 2 or 3 months. So out of 12 months, it occurs in 2 months, and the remaining period is dry. So that is what is roughly said by this 80% of the rain occurs in 20% of the time. Huh? Yeah. No, I know that this is true, but there is sort of more uniform rain here, or actually near the equator, it is slightly more uniform. But roughly speaking, it is true still. Then, if you look at those 3 months, even in those 3 months, most of the rain will occur in 20% of the time. 80% of the rain in those 3 months will occur in 20% of the time. And I go down from months to days. In one day, some rain occurs, but that rain will occur not in 1 second, but will occur in 1 or 2 hours. After that, it doesn't occur. So this observation that 80% of the rain occurs in 20% of the time is more or less true over lots of scales of time. It is true not beyond 1 year, but from a year up to an hour, it seems to be true. Okay? People have measured rain nowadays at the time scale of milliseconds. And it's very local observation. They take some small rain gauge and they measure how many drops of rain have fallen there, automatic system. And then they plot a similar graph and it looks similar. Okay, let's not get into the details of that stuff, but I'm just pointing out that this phenomena is very general. Some of it is your everyday observation as well. Like when I said that, 80% of the rain occurs in 20% of the time, that was not a big surprise for you. Okay, so in the end, the problems we are studying are related to our everyday experience. Okay, I think that is very important to realize, because sometimes when we study some models in mathematics, the connection to everyday world is very much lost. You define a function R, I don't know, it goes F colon R goes to R is a function. I don't know what it is. So sometimes the mathematicians are proud of the fact that they don't know what they are talking about. It's true for whatever F is. Okay? There is a generality, in that description. But for beginners, it is useful to have an interpretation available. And you know that when I'm talking of F, I'm talking of the price of the cloth of length L or some such thing. Okay? Then things make much more sense. And okay, some of the results are generalizable to other functions, but let's not worry about that just now. So that is a sort of longish introduction, but let us start with that. Okay. So now, this is number 2. It is a model of Sandpiles. Okay. So instead of real Sandpiles, we will start with a simplified model of Sandpiles. Okay. So, this is one of the things scientists and also mathematicians do often, is that they study simple models. And that is supposed to be a joke, or people don't make fun of it. It is called the spherical cow approximation. When people want to make joke about it, they say you can approximate a cow by a sphere and then study all kinds of properties. Okay? But actually the origin of that story, it's an excursion. But I think it is interesting, so I'm making some detour into things which are not fully relevant to Sandpiles. So there was an Arab sheikh, and he had lots of horses. And he hired a person, nutrition expert, to decide what kind of food should be given to the horses. And so that guy wanted to make some understanding. The horses also are different sizes, and so this guy wanted to make an estimate of how much food is needed by a horse. So he made some theory that you have this kind of temperature and they lose heat, and so every day they must get energy equal to the amount of energy they lose through heating or some work or some such thing. And so they said that, well, if I'm going to estimate how much heat a horse loses per day, it is good enough to approximate him as a spherical object of that shape and mass. And actually it's not a very bad approximation. Okay? If you say how much heat is lost by a horse, is not very different from how much heat is lost by a sphere of the same mass and same temperature. So it's a good approximation. It is not a stupid approximation. Of course, it is not the real thing, but it's pretty good. Good enough for my purpose. That is the attitude we will take. So this model I'm describing now is not working with real sand. It's a model. It's an approximation. You can always make a better approximation, but there is no reason for making fun of it as only a simplified model. Okay, very good. So what is this simplified model? This simplified model is called wooden blocks on a staircase. So I have a staircase, You can draw it slightly better, but you see, this is a roughly picture of a staircase. There is a child sitting at the top of the staircase. This child has wooden blocks with her, okay, and she drops them down. So she throws the wooden block, and the wooden block comes and sits here. Like that. Okay, and then she has another block, she throws it, and it will come and sit there. She keeps on throwing. I don't know if you have any small children, seen any small children, and they do this, they keep on throwing stuff. And so, she throws it from the top, and then what happens is that if, suppose another block comes on top of this one, then these are slightly wobbly, and they become unstable, and they topple, and they fall down to the next level. So this thing will fall down to the level here, and they will come and sit here. And then she keeps on throwing, so some other time, some other thing will come on top of this, and this will topple, and will go down further. Okay, and so we will say that if two blocks come on top of each other, they fall down to the next level, and they fall down on adjacent sides. So this one will go here and one will come here. Okay, and that's all. At the bottom, there is a mother who is very patient and hardworking, so she keeps on removing all the blocks and resupplying it to the baby on top. Okay, so that is my model. So what happens in this model? Well, it is not very bad. It is approximately what happens in sand piles. Suppose you take a sand pile. So firstly, I don't have to work with conical sand piles. I can work with sand piles which look like this. Just a surface which, flat surface of sand. Okay. Then what happens is, all the sand which is below does not move much, and you drop sand here, it goes down there, and you drop sand here, it goes down there. Sometimes it stops, sometimes it goes in an avalanche, but all this occurs on the surface. The stuff below is deeply buried grains are not moving much. Okay, so I approximate. I just say, okay, these things are not moving at all. They form the staircase. And the topmost layer is the grains which are sitting on this below part which is not moving, which are the movable grains, and they fall down. So I keep on adding here, and whenever there are two things on top, they will fall down, and then they will, maybe this thing falls down, but it falls on top of some pre-existing grain, then it will fall down even further, and it will cause an avalanche. Okay, so the model is very clear. The fact that if you add at random on top, you will cause events of various sizes, because sometimes you may add on something which is already there, sometimes you may add on something which is not there. If you add on empty site, it will just sit there. If you add on a site which is already a grain, then it will go down. But suppose I add on a site which there is something here, they go down to two sides, but these were empty. They'll just go and sit there, right? But suppose there was already a grain here, then this will fall down here, but then this will cause these things to fall down further, right? So you will have an avalanche of variable sizes, sometimes of size 0, which means nothing happens, sometimes of size 1, which says one toppling occurs and then nothing happens, or maybe two topplings occur and nothing happens, and so on. And so in my simple case, I am saying that this looks like sandpiles to me, and I want to understand what will happen in this system. So what will happen? So first concept, is there is a notion of a steady state, which says that I have this staircase and I keep on adding grains on top. Let's say one block added per 10 seconds. Okay, so I keep adding one grain per 10 seconds, and then they will fall down and they will fall down and they will be removed from the bottom. So after a long time, what will happen? The system will be in some state where some grains are here and some grains are, some places are empty. Then I come back after 2 hours. The state of the system will look the same, qualitatively the same. Okay? This is a very important notion. It's not exactly the same configuration, but I don't look very hard, then it looks to me the same. Okay, so that is the notion of the steady state. It has been deliberately described in a very vague words, and I hope you can make out exactly what do we mean by a steady state. What it means is that there is a possible configuration C of this system. And it's not in a fixed configuration, but there is a probability that it will be in some configuration. And this probability is not changing with time. After 1 hour it is something, after 2 hours it is the same. And so if I look at the behavior of the system, it looks the same after 1 hour as after 2 hours. Yes, sir. Yeah, probability of what? Very good. Whatever you want to study. I want to study what is the probability that nothing will occur. It will tend to a fixed limit value, independent of time. Just 1 second. And if I take, after 1 hour it has some value, after 2 hours it has the same value. I will ask what is the probability that the event is of size 5, not size 1, and that will also tend to a limit, which is independent. Yes, sir. Yeah. Yeah. No, so actually the notion of a steady state is much more general. So it says whatever question you want to study, it will tend to a definite answer probabilistically. Okay? So I don't care about sizes of avalanches. I can look, what is the probability that you see a structure like this? There is 1 grain here and below that there are 2 grains. That will also tend to a definite limit. Okay? All of these are encoded in the statement that steady state is specified by probability of a configuration C. The system at time t occurs in a configuration C. C is a random variable. C is the configuration, it's the state of the system. Okay? So I don't know after 1 hour which state it will be in, but it has a probability to be in some state, and this distribution will be the same independent of time. So just to be sort of sure of the idea, suppose I take a tube like this and I push water through the tube. Okay? So after some time, this water just flows through here and goes out here. But if you push it hard, then it is turbulent flow. And the water doesn't come out uniformly. Sometimes some more water comes out, sometimes less water comes out. But the probability that you will see some kind of a structure is the same. Okay? So in the case of turbulence, people will plot similar thing. It's called flow as a function of time. This is turbulent flow, and particular shape you get will be not reproducible again. Next time you do the experiment, you will not get exactly the same shape, but the statistics of these shapes is fixed. Okay, I'm not fixing that, okay, the flux has to be this value here. You can ask what is the probability that two adjacent peaks occur, whatever that means. And that will also have a, so long as the question defined is proper, the answer will be fixed. Yes, sir.
So, but like if you're having a sand pile set and you're pouring like sand, extra sand at like 10 grams per second,
Yeah.
then the system is not in a steady state.
No, as I said, it was very important that there is also a mechanism for excess sand drops out. There is a fixed boundary and excess sand drops out.
Like if we are assuming that the sand just piles up on the.
So in the case, in this experiment, there is this table, circular table, and the sand pile looks like this. If you add extra sand, it will come here, but some sand will eventually drop out, and at large time there is a mean mass. It doesn't grow indefinitely, it remains finite.
Yes, sir, but when you're adding 10 grams per second,
Yeah.
the system is changing.
No, so certainly the mass is a function of time is not constant, it fluctuates. Sometimes it's more, sometimes it's less. And we are trying to understand these fluctuations.
So then in this case, is the system in a steady state?
Yes. Actually, it is not always in the steady state. If I start with empty table, then initially it will just form something, but eventually it will reach a steady state. Just 1 second. What happens initially depends on how you prepare the system. But sometimes the initial state does not matter, and the long time steady state is independent of preparation. And that is the kinds of systems we are studying now. Yes, sir. The behavior in the steady state is the same after 1 hour as after 2 hours. That is meant by steady state. And we are trying to determine what it is. We are trying to characterize it in a whichever way I like. I'm not stuck to calculating probability that there will be an avalanche of size 5. No, whatever question you want to ask, you can ask. But that will be characterizing the steady state in some sense. Yes, sir.
So here the base determines the time taken to reach a steady state.
Yeah, of course. So, in fact, it doesn't have to be a circular base, no. The base can be like this. If I take this base and I make a pile on top of it, what will be the shape of the pile produced? It's a funny shape, slightly complicated, but it is governed by the principle that the shape will look like something like this, whatever. Okay, I cannot draw very well, but the local slope everywhere will be the angle of repose. That is the condition which determines what is the shape of the pile. Yes, sir.
So an infinitely big base will take infinite amount of time to reach a steady state.
Yeah. So we always work with finite systems. Okay, I think it's very important. In some mathematics stuff, people want to study infinite systems, but most of the problems become much harder to understand if you take infinite size limit first. So the system never reaches a steady state. Then I can study those systems also, but it turns out that the steady states are easier to understand than the other part, which is transient states, which are complicated. Okay, so first let us understand the steady states of finite systems. Okay, very good. So actually this is sort of aside, but suppose I have an elliptical base. Instead of circular base, I have an elliptical base, and I pile a sand pile on this. dry sand, what will be the shape you will get? Can you make a guess based on what you know now? No, it's not a cone. Yeah, it is sort of like a mound, that much is correct. I am saying I start with a base which is elliptical, not circular, and I make a dry sand pile on top of this, and what will be the shape of the pile? I pour uniformly all over the area. Elliptical, no, you don't get an elliptical cone. The condition for the stability is that the angle is the same everywhere. The angle of repose, which is the local angle to horizontal, is the same everywhere.
Will we get 2 peaks?
Okay, this one is, I will draw the answer for you, and then you will realize that, okay, this is what must happen. There is sort of some shape, and on the top there is a ridge line. Okay, and you can actually calculate the shape of this exactly if you like, and that's an exercise which I am not doing here now. But you know, you can say that how will I determine the shape of the pile, given that the constraint is that the angle is always the angle of repose. In this case, on the sides it looks like a cone, but on the top it looks like a ridge with slope with discontinuity in the angle. And it's not one point which is singular, it's a whole line which is singular. And this line doesn't extend all the way up to here, it stops somewhere in between. And if I make the pile closer to a circle, these 2 points will become like this, and you know, and in the end they become 1 point. That is the cone. Okay, all right. This was an aside. Let us get back to the original problem. Okay, original problem. So now, since I am going to work with this particular model, let me make it more, let us introduce some notation or the way to describe the problem. So I will describe it like this. Yeah.
Is it mathematically possible to calculate for a given shape,
Hmm.
base shape, is it mathematically possible to calculate the point for any given shape? Like how the structure is?
I don't know. I think it is possible, but obviously the answer has to be sort of understood in some sense. I can always say that, look, this is the equation satisfied by this thing. If you can solve this differential equation, that's the answer. Okay? But can the answer be found in closed form? That will be possible for some lucky shapes. I think for an arbitrary shape,
What is closed form?
closed form means that it should be expressible in terms of Bessel functions or some functions which have already been defined by other people.
You have a fixed formula which will actually give you the answer. Like it's not just that a formula.
Yeah, no, I think this is an important point, so let me discuss it a little bit. Let's look at this integral. This is an integral. It's a definite integral. It has a value. This much I know. I can evaluate it numerically. But maybe I cannot write it in terms of Bessel functions or Jacobi functions or theta functions or one of those functions that are there in textbooks. Okay? So usually, if you expect the answer to be expressible in, this is an answer, I equal to this is the answer to my problem. Okay? But some people are not satisfied with this answer, they want the answer in closed form. It is 2 by root pi or not? It's not 2 by root pi. Okay? So one should get out of the mode where you think that the answer is only there if it is expressible in closed form. Sometimes the answer is expressible in terms of the definite integral, or as a solution to a differential equation, or for example in the much older stuff there is a 5th degree equation. What is the solution of this equation? There is some theorem says it is not expressible in closed form. But there is a solution, or there are 5 solutions, or whatever it is, right? So if you insist on the solution in closed form, even this simple equation has no solution. No, it has a solution, only I cannot write the solution in closed form. Okay? So we will perhaps not always be able to express the solution to my problem, which was that there is a base like this. What is the shape of the pile on top? In closed form. But maybe I can solve it as well as I wish, numerically or in some way or the other, or whatever. For example, for this equation, you can write the answer to 15 or 35 places of decimal if you wish. Yes, sir.
So if the function doesn't tend to like infinity, we say it's closed form.
No. Closed form means there is a formula such that you feed, it's expressible in terms of known functions. So x squared plus x cubed, these are simple functions. You can have functions which are square root of x squared plus 1, or sine x, cosine x, those are all closed forms. I can have a solution which says
Roots of a quadratic also, right?
yeah, roots of a quadratic also are closed forms, but roots of a cubic are also closed forms, it turns out. But roots of the 5th degree equation cannot be written in closed form. Closed form is just a sort of saying that, is it something I have seen before? Maybe I haven't seen it before, maybe nobody has studied this equation before, in which case it doesn't have, the solution is there, but it doesn't have a name. It's not going to be root pi, going to be something else, and it doesn't have a name. The best way to describe the solution of this equation is to say that it's the solution of this equation, it's the largest positive real solution of this equation, or whatever it is. Right? I suppose this equation doesn't have a positive real solution, but whatever.
So that integral is basically a solution for any basis that one is.
This integral is there is a problem, and this is the answer to that my problem. Okay? But it doesn't have a closed form solution. So for example, Edison at one time, he was making electrical bulbs, and he wanted to optimize the shape of the bulb. So he asked somebody that, okay, I have this bulb of this shape, can you calculate the volume of this bulb? And this guy kept on working for so many 5-6 days, and he couldn't get a closed form answer for the shape, for the volume given the shape. And Edison said, oh, I just put some water in and measured the volume of the water, and that is the solution. Okay? I think it's very important not to get stuck with closed form solutions. They are not the only beautiful things. This answer is pretty good, whatever it is.
So what is the solution of?
Right now, I didn't tell you the problem, but suppose there is a problem whose solution is this. Would you be satisfied? Yeah, this is an example. So what is this good enough for me? I would say it is good enough for me, because I asked that, okay, there is this sand pile, what is its mean height? And mean height is this number. Whatever, some problem or the other, the answer is this. I would say that I can calculate this answer to 15 places of decimal, so it is good enough for me. It's not a closed form solution in the way closed form solution is understood, but I have solved my problem. So one should go beyond the notion that the solution of a problem means a closed form solution of the problem. Okay? Anyway, let's go on. This is my, so I start with a lattice like this. Each side has two sides below it. And here, below this, there is nothing. So sides below it are absent. Okay? Now we will define, and this is L, and this is M. So L is here 1, 2, 3, 6, and M is 4. 6 by 4 lattice. Right? On this lattice, I will define my sandpile model. So at each side, there is a variable called Zi equal to 0 or 1. I is a site index. So for me, the site index is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. You label them. The index is just a label of the site. It doesn't have any other function. Okay? So every site 11, the lower labels are 17 and 18 or whatever. Okay, I can put 19 here, it doesn't matter, 20 will be here. These are just labels. Okay, so every site has a height which is denotes a stable configuration of the sand pile. So at each site there is either 0 particle or 1 particle present, 1 grain of sand present, and these are stable. But sometimes Zi can become bigger than 1. If Zi is bigger than 1, then its site is called unstable, and 2 particles drop down to sites below. So toppling rule. If Zi is bigger than 1, then Zi goes to Zi minus 2, Zj goes to Zj plus 1 for j below I. There are 2 sides below it. Each of the sides, the height increases by 1 because those particles come and sit there. Is this clear? Sorry? Yeah. Toppling rule. So it says that if the height at the site is 0 or 1, it is stable. That site is stable. But if the height is more than 1, then 2 particles will topple and go down below to the lower sides and sit on top of them. Okay? As simple as that. So Zi goes to Zi minus 2 if Zi is bigger than 1. So it can become 0, but it cannot become negative, I guess. And the sides below, j below I, it will become plus 1. Okay, so now it is 10 o'clock. We can take a 5-minute break if you like. And some of you can go out and do something, or some of you can see if you understood whatever was said so far, and then we can meet after 5 minutes break.